Hey guys, so I just wanted to put together a quick tutorial video to help you guys kind of get started on developing some low-level drivers for either the flight computer or the liquid engine controller. So as you can see from this diagram right here, this is a visualization of the embedded software stack. So basically at the bottom here, we have the actual hardware itself, the microcontroller and its peripherals. And then on top of that, we're using a third-party library called CMSys, which I believe it stands for Common Microcontroller Software Interfacing Standard or something like that. And basically, it's just a library provided to us by the microcontroller manufacturer to kind of help us with accessing some of the lower level registers and stuff to actually touch the hardware itself. So this HAL library basically gives us a set of APIs that we can use to access the I2C, UART, SPI, GPIO, etc. hardware. And this is none of this is code that we write. This is all library code, and as such, it's stored in the lib folder within our repository. And then on top of that is where the drivers are implemented. So you can see these are all names of either current drivers or drivers that we will write in the future, which are going to be calling the API functions within the CMSys library to actually do stuff like talk to chips over I2C, or access the memory in an SD card using the SDMMC and stuff like that. So how do we actually go about initializing the microcontroller to do that? Well, there is this document here called, let's see if I go back to the top. It's called HAL documentation.pdf. And basically what this is a user manual that will describe how exactly you use the CMSys HAL library, what API functions are available, what type of data types do they use, all of that fun stuff. So it's obviously a pretty lengthy document, although you don't have to read the whole thing, obviously. So like, for example, if we're going to generate some I2C code, we might go to section 33 right here, which will tell us all of the data types used within the I2C driver. And it'll also give us a step-by-step instructions on how to initialize the driver and then use it. So in theory, all we would need to start writing initialization code for the microcontroller is this document here. However, this initialization code tends to be pretty tedious, as it involves just filling up these massive structs with all of our microcontroller settings. So we rely really heavily on this code initialization tool called STM32CubeMX. Basically what that allows us to do is it gives us a visual display of the microcontroller and allows us to use a GUI to kind of set up certain settings, and then it'll generate the code that implement those settings using this HAL here. So some documentation that you're going to want to be able to reference here is obviously this document, as well as some other stuff here in the design folder on the Google Drive, such as the schematic. So this is where you would see all of the, let's see if I can open it up on this other tab. So this is where you would see all of the microcontroller pin connections. So when you're writing your drivers and stuff, if you need to initialize like a new interface like I2C, you might have to come to the schematic here to see what pins the device that you're trying to work with is physically connected to. There's also the firmware documentation, which this is where you will be documenting certain decisions that you make on like microcontroller settings and whatnot. So you can see here we have this clock configuration section of the document where we document what numbers we're using for prescalers and phase lock loop multipliers, just so that in the future, if we ever need to figure out why a number is the way it is, we can see why we originally decided that with kind of like a paper trail. There's also, if we go back to the drive here, there's also the bill of materials. And so the bill of materials is just this big old spreadsheet that contains information on every single component that is a part of the board. And so this is where you can access the data sheets as well. So like if you're looking for the IMU, you can Control F and go IMU. And then, once you're here, so you get the IMU, and then this link right here actually takes you to the data sheet. So if that'll load, and so these data sheets will be really important when we're writing low-level drivers, because they're going to tell us exactly like what type of byte sequences do we need to transmit over like the SPI peripheral in order to, get data off of the chip or to program the chip in a certain way, and all of that fun stuff. So you'll definitely need the data sheet for the part that you're working with, and you'll document all the decisions you make in the firmware documentation file, along with and you'll use the schematic to figure out what's connected to what. There's also some other stuff here, like the microcontroller data sheet, the data sheet for the actual programmer, and then the programming manual, which talks about all of the really low level stuff with the stack pointers and the assembly language and all that fun stuff. But for the most part, you'll primarily be concerned with the schematic, the HAL documentation, and then the data sheet for the actual part you're working with. So that's hardware, or sorry, that's documentation. So let's start talking about code. So the first thing you're going to probably do when you're writing your driver is you're going to generate some initialization code for the part that you're working with. So if we go to my terminal here, so I've already navigated to where my flight computer firmware repository is. But once you're in the repository, you want to run a Git Status, see where you're at. So I'm on the main branch right now. And before I actually do any development, what I want to test is to see that I just want to make sure that the main branch is building correctly, because if it's not building correctly now, and then I try to write a bunch of code, and then it doesn't build, I might not be able to figure out why it's not building. So it's always a good idea to just run the build on the main branch, just make sure it's stable before you start building on top of that. So this is looking good. I'm not seeing any errors. So the main branch is good to go. So we've checked the main branch. So, as I kind of mentioned, we want to keep this stable. So when we start writing our own code, what we're going to want to do is make a personal branch, develop on that branch, and then once that branch is good to go, then we merge it into the main branch. So I'm going to create a new branch, which I'm just going to call Colton / demo driver. And so you always want to start your branches with your name. That way that we all know whose branch is what. So I'm just starting it with Colton here, and then you want to kind of name it something descriptive to kind of give an idea of what's on the branch. Don't just name it new branch or something like that. Definitely. So like if you're building the IMU driver, I would maybe call it IMU driver. But I think that branch already exists, so I'm just going to call it this one demo driver. So I made a new branch. So now I'm good to go to start coding here. So I'm going to navigate to the program. So I'm going to go to where I have the program installed, which is in this folder. And then I'm going to actually launch the STM32Cube MX tool here. Obviously I'm on Linux, so I have to go to the terminal and find it. But if you're just on Windows, you can just launch it via the desktop icon or searching for it or whatever. So this is what it looks like when you open it. And so what we're going to do is we're going to actually load the current configuration by going to this file tab and then hitting load project. And then once you kind of open up this, you want to kind of navigate to where the repo is installed on your computer. So for me, it's in documents, SDR, firmware, and then right here in flight computer firmware. And then for kind of our low-level module development, we're working on the terminal application. That's kind of what we're using to test everything. So we're going to be in terminal revision 1, and then this auto folder right here. So the auto folder is where all of the auto-generated code is going to go. And so we're not going to physically touch any of the code in this folder. We're just going to let the tool do it. And then we copy things we copy what we want to copy from the auto-generated tool into our code files, which are either going to be just in this folder or in the config or mod file. So if I go into that auto folder, there's this .ioc file here, and this is just a file type which is specific to this tool, which contains all the information that the tool needs to generate the code and understand kind of what the processor configuration is. So if we go ahead and open that, it'll take a second to open here. Yeah, we'll just wait for that to load. Might take a little bit longer the first time you launch it because it'll probably have to download some stuff, but it shouldn't take too long once you've done that. So here we go. So here's what the tool looks like. And as you can see, there's already some configurations that have been set up just because we loaded it instead of starting a brand new project, which is kind of part of the streamlining process I've been working on today. So you can see, like, I already have some SPI pins set up. That's for the actual flash chip that's on the flight computer. This USART here is actually being used for the USB, and these GPIO outputs are the LED, and then this is the external oscillator, which is what we use as the source of our clock signal. But I'll do this tutorial assuming I2C, as that's probably what most of the new drivers are going to be using. But you would do the same-ish procedure for whatever peripheral you're working with. So the first thing that I would need to do in order to set up this tool is figure out what pins I'm actually using for my I2C interface. So for that, you have to go back to the schematic. And once you're on the schematic, you go to the piece of hardware that you're working with. So like I'll just do this tutorial for the IMU. So if we go to the IMU here, we can see that the I2C pins, which are SCL and SDA, are attached to this label SCL and SDA. Pretty simple, right? So we'll go up to the microcontroller, and we have to figure out which pins those labels are attached to, and they're right here. So our IMU is attached to pins PB6 and PB7 of the microcontroller, which in the physical layout, those are pins 92 and 93. So if we go back to the tool here, that's PB6 and 7, which are right here. So if we click on the pin, it'll give us a drop down here of all of the different peripherals that I can use this pin for. And I'll just go ahead and select I2C1. And I'll do the same thing for the second pin here, which is I2C1 SDA. So you can see the tool now recognizes that I want to use these two pins. However, they are highlighted in yellow, not green. Which means there's still some stuff I need to do to set up a valid configuration. And what I actually have to do here is I have to actually enable the entire I2C interface. So to do that, I go over to this connectivity tab, and I click on I2C1, and that gives me the current configuration. And as you can see, it's disabled. So from this drop-down menu, I can just click I2C, and now it's enabled. And then here I get the configuration, and so these are all of the settings that I can play around with to customize how the I2C interface on the microcontroller works. I'm not going to change anything here just for simplicity, but some settings that you probably will care about are the clock frequency. So right here, it's just 100 kilohertz. Depending on what the chip is expecting, you may have to change that, or you almost certainly will have to, but I'll just leave it at 100 here for simplicity. And then the other thing you probably might have to, or the other thing you might have to tamper with is this address length. So like the way I2C works is every device on the I2C bus has like a unique address, and that address gets transmitted at the beginning of a communication. You'll transmit the address over I2C to all of the devices on the bus, and then whichever device corresponds to that address you've just sent will know, okay, the microcontroller is trying to talk to me now, so I should listen to whatever data comes through. So I think most devices should just use 7-bit, but if you need to change it to 10-bit for whatever reason, that option is available to you here. But so yeah, so now we have a valid I2C configuration. So now we just got to check the clock settings. So here's the total clock configuration for the entire microcontroller. So you can see I've already played around with some of the settings here to make the CPU frequency the maximum of 480 megahertz, and then the SPI is 24 megahertz. So this number down here is what we care about, which is the I2C clock, which right now is at 120 megahertz, which I don't really see any reason to change that, so I'm going to leave it. However, you could mess around with it by changing which value is going to this mux here. And that would require you to mess around with this third phase lock loop. As you can see, if the configuration is invalid, you'll have this pink highlight, and if you hover over it, it'll tell you why it's invalid and how to change it. So just keep in mind, if you have any pink settings, it won't let you generate the code until you resolve the issue. So I'll leave it on the default for now for simplicity. But yeah, when you actually do this, you're going to want to try and not change as many settings as possible, because, like, for example, this phase lock loop here is set up for this 480 maximum frequency, and this phase lock loop here is set up to get this 24 megahertz frequency on the SPI for the flash. So try not to change those. If you do have to change them, let me know, and we'll try and work something out and find a solution that works for all of the chips. But if you can find something that works without doing that, that's probably the preferred way to go. And then before we generate the code, I want to re-emphasize that all of these decisions you make in the tool here need to be documented in this firmware documentation doc. It's pretty easy, with this GUI interface, to just start playing around with numbers and then forget what you set and why you set it, or if a certain value you just played with it and then didn't change it back. Down the line, we may be left wondering, well, is that number something we actually wanted to set, or did that just get accidentally set for some reason? So if we document everything we do, that'll make it easy to resolve those issues. So just if you change any of these settings, just make sure that within the firmware documentation, somewhere you document what you did and why. So then there's also this project manager tab, which kind of keeps track of like where the files go and whatever. The two things that are really important for you to notice are the project location, which should get updated when you actually load the file. If you run into issues, maybe just make sure that file path is correct, but I don't think it should cause any issues. And then the other thing is just make sure that the tool chain is makefile. You can use some of these other tool chains if that's more convenient for your setup, but when we actually start merging code into the main branch, it will have to be a makefile to ensure that everybody can run the code and not just people who are using your particular IDE setup or whatever. So yeah, so to generate the code, we can just go hit generate code, and it will update our code. So we'll just wait for that to finish. Okay, so it's done. So now what we can do is we can go back to our repository and look at what the code generator did. Okay, so I'm in the terminal directory, and so the best way that I think to figure out what the code generator did is to run a Git Status. and it'll show you, within the auto folder, which of these files actually changed. And so what we care about are the code files. So that's going to be these two right here. So you can see that Git is telling me that the code generator changed my main.c file. And it also changed this STM32 HAL MSP file. The make file changes every single time, so that may or may not correspond to a valid change, but you'll have to check it just in case. So what I'll do here to copy paste things is on the left, I'll have my the auto-generated code, and then on the right, I will have the actual terminal application code. So I'll just go ahead and real quick on this other window, navigate to where the code is. So as I mentioned before, all of the auto-generated code is in this auto folder. And then more specifically, all of the C code and the header files are in this core directory, whereas the drivers contains all of that library code I was talking about earlier that we don't want to touch. So within core, the C files go into SRC and the header files go into Inc. So Git tells us that we only updated C files, so we'll just stick in this SRC directory for now. And we'll start with the main file here. So here's what main.c looks like. And then for the actual terminal code, we'll open up our main.c. Okay, so now that we're into the main.c file, we can start looking for differences here and copy pasting what got inserted. So you can see here, actually, we have this new variable here of the type I2C handle type def called HI2C1. And so this is actually the handle for passing in arguments to the I2C API. So we can go ahead and just copy paste that into our application code, and then just include a little comment here so we know what this is. So we'll just say this is IMU I2C handle. Okay, and then we got some function prototypes here, and we didn't touch GPIO, SPI, or UART. But we did touch I2C, so we need to copy over this new function that the code generated. And then I'm also actually going to change the name of this function because I2C1 is not a very descriptive name, so I'm going to call it IMU I2C init. That way, when I'm looking at the code like 3 months from now, I don't have to remember which I2C peripheral I'm using for the IMU. Okay, so I got that. Now we go into the actual main function here, and we're actually calling that initialization function. So I'll go ahead and just write that in here with the new name. We got that, and then there shouldn't be anything in the main while loop, so we should be able to just scroll down to system clock config. So system clock config is going to correspond to all of those settings in that really big circuit schematic that we were looking at earlier with all of the clock frequencies. So we did not actually change really anything at all there. So if we look at this code, there's really no differences between the two. So we don't have to update anything. However, if you did change that, so just going back to the tool really quick, if you did change any settings in here, then that code is almost certainly going to change. So just make sure you go through that code and figure out what has changed and make sure you update it. One thing you can do to make this process more efficient is if you check out another version of the repository, you can stay on the main branch. And then you can run like a diff tool to see the difference on a file per file basis between what the code generated every time, and that'll help you find like which of these lines of code is different real quick, instead of having to like look through them and manually change them. But there are some stuff that's going to be pretty obvious, like for example, this I2C initialization function, that obviously did not exist before we ran the tool. So we will go ahead and just copy paste that over into our terminal application code here. And then I just got to get rid of some of these copy paste artifacts that the Vim software, for whatever reason, just puts into my files every time I copy paste something between files. And then another thing to keep in mind here is that you can see that the auto code generation tool generates the code with a slightly different formatting than like what I've been using for these functions. As you can see, I got this big old header here. So actually, when you go ahead and you do this, I'm going to ask you to update this formatting so that it matches the rest of the code, which might be a little bit tedious, but it goes a long way to making the code a lot more readable. So if you try and merge code that has this like user code begin in here, I'm going to look at that. I'm going to tell you to change it before you merge it. Okay, well, we got the, oh, and then the other thing we need to do here is we actually changed the name of this function. So I got to change this name from mx I2C1 to IMU I2C. Might as well just get rid of some of these unnecessary comments. Okay, and then going back to the auto-generated code here, we didn't touch the SPI, so we should be good there. We didn't touch UART, so we should be fine. Gpio, you're going to want to check this every time, no matter what. However, it shouldn't have changed for us, since we don't need any Gpio for I2C. However, it's always a good idea to look at it. So we've got all of the same Gpio clocks are being enabled. And so just looking at the code, I know just off the top of my head that, you know, pin 10, 11, 12 are the LEDs. So we didn't touch these pins. Also, I guess if we just go back to the tool, you can just look at this tool, and we only touched these two. All of these other pins already were configured. So if we just look at, we say, oh, okay, pin 10 was one of these ones that was already configured. So this code doesn't really correspond to me. Or use that diff tool again, like I previously mentioned. But so yeah, all of these pins here were stuff that already existed. So we don't need to edit anything here. And that's actually it for the main file. So now that we're done with the main file, we can move on to that STM32H7 how MSP file, which was the other one that Git told us had changed. So we open that up, and then for our terminal application code, that's going to be in the config folder. Config source to be more specific, and then we can open that up. So let's look at it here. So the first function we got is how MSP init. So just looking at that, that's the same. So we're good there. And then we've got an I2C file or full function. So we're definitely going to need to copy that one over. So I'll go ahead and do that here. And then, like I mentioned before, when you actually do this, you're going to want to go through and update this formatting to be consistent with the rest of the file, but I won't do that now. Okay, so we I2C MSP init, and then there's also an I2C MSP dinit function. So we'll copy that as well. Okay. And then we can look here. So we got SPI, we did not touch SPI. And then UART, we did not touch UART, and that's it. So now we're done with our copying and pasting, so we can exit out of these files. And we can go back to our main directory. So the last thing to do is just to verify that our make file is okay. So it doesn't, I don't think the make file has every single driver.c file included in here. So probably just the thing is just to make sure that the files corresponding to whatever interface you're using are here in this list. So just looking at this, we can see that I2C is right here. So we're fine. We don't need to edit the make file. So the only thing left to do now is to compile it and make sure it compiles without error. So we'll just run that compiler there and things are looking good. No errors or warnings. So that means we're good to go. So at that point, now our microcontroller is now properly configured to be able to do I2C stuff. So from this point, it would just be actually working on the driver functions and using those I2C how functions to do that. So that's about it. So, from this point, if there are any questions on that or anything I did, it was kind of confusing or a little bit too fast, feel free to reach out to me over DM or whatever. But anyway, that's about it for this video, guys.